Second-order linear ODEs, very cool, but what are we going to do with them? How do we solve them? Second-order ODEs is not so obvious. We've seen a couple examples where we guess at a solution, but it's not obvious how to proceed in a principled manner. Well, here's an idea, a really cool idea that uses the differentiation operator to solve second-order equations and a whole lot more. This is very cool, but it's going to require us to recall, think back to the end of Volume 1, where we introduced the notation capital D as a differentiation operator. And one of the things that was so cool about these operators is that you could do algebra with them. Because we're working with differential equations whose solutions are of the form x as a function of t, let's let this differentiation operator, capital D, denote differentiation with respect to t. So it's d by dt. Then if we want to encode the second derivative, we could think of that as d squared. That's differentiation twice. For higher derivatives, we could take higher powers of d and then apply it to our function x of t. If we take d and raise it to the 0th power, this means we differentiate 0 times. That has a special name. That is the identity operator, capital I, which does nothing. This notation has a lot of uses, but it's especially powerful when it comes to solving linear ODEs. Let's start with a simple example, going back to the first-order ODE that we all know and love. If we think about dx dt equals lambda times x, let's convert this to operator notation. dx dt becomes d applied to x. Lambda times x doesn't really have a derivative in there. Oh, but wait, you're differentiating 0 times. I could think of lambda x as really being lambda times the identity applied to x. Now here's where it gets cool. Let's move everything over to one side of the equation so that we have capital Dx minus lambda times the identity applied to x. That is equal to 0. If I factor out the x and think of a single operator applied to it, that operator is really d minus lambda times I. I'm going to think of that as a single differential operator that is applied to this function x, and that kills it, that sends it to 0. Now, based on what we already know, we observe that the solutions, the set of functions x that get sent to 0 when hit with this first-order differential operator, d minus lambda I, are precisely the functions of the form some constant times e to the lambda t. Now, that's not telling us anything new. This is something we already know. It's just translating it into a new notation, an operator notation. But watch this. Let's move from a first-order linear ODE to a second-order linear ODE. Let's use the example we looked at recently. The second derivative of x minus 3 times the first derivative of x plus 2x equals 0. That's a second-order linear ODE. Let's convert this into something that uses operator notation. That second derivative converts to d squared applied to x. The next term, minus 3 times the first derivative, that's minus 3d applied to x. And then the last term, of course, is just 2x. Add those things together, set them equal to 0. That's our equation. If we want to follow the same pattern that we used in our first-order example, let's factor out the x on the right and apply a single second-order differential operator to it. That factorization will yield, as that operator, d squared plus 3d plus 2i. Apply that to x, you get 0. Now, what's cool about this is you can see that this is a polynomial in this differentiation operator capital D, and polynomials can sometimes factor nicely. Can you factor this polynomial into a product of first-order terms? Oh, yes. Absolutely. Not a problem. Let's do that. Let's factor that second-order operator as quantity d minus I times quantity d minus 2I. And we just check it in our heads, first, outside, inside, last. Yes, that works. That works fine. And following our intuition of how algebra works, if applying the product of these two first-order operators to x gives us 0, then that means that either the first one applied to x equals 0, or the second one applied to x equals 0. Now, this is really interesting because we know how to solve these first-order problems. If I take d minus I, apply that to x, get 0, what does that mean? That corresponds to the first-order linear differential equation dx dt equals x. And we know how to solve that. That as solution x of t is some constant times e to the t. If I solve the second one, if I say, oh, no, it's really d minus 2I applied to x equals 0, then the solution to that is going to be what? That's going to be some constant times e to the 2t. Why is that? That's because this first-order differential equation corresponds to dx dt equals 2x, and we know how to solve that. Now, we have this situation with two possible solutions, each involving a constant. They are not the same constant. I call them both c, but these are really independent of one another. There is an or operator, a logical or between these two, which means that we can take combinations of these solutions, these basis solutions. Because differentiation operators are linear, that means that adding these two together and hitting them with these differential operators, you're still going to get 0. So the full solution to this second-order ODE is going to give us x as a function of t is some constant, c1, times e to the t, plus some other constant, c2, times e to the 2t. You can check that anything of this form solves that differential equation. You may recall that when we looked at this equation previously, we guessed at a solution that happened to fall under this general form. Now, this idea of using differential operators and factoring them into first-order pieces, oh wow, this is such a wonderful idea. It's so useful, as we shall see. Now, we're not going to be able to explore this method in full generality, in part because you need a lot more algebra, linear algebra, in order to really get into how this works and why it works. Suffice to say for now that it's really the linear nature of these second-order differential equations that is allowing us to use this operator technique.